Today is way hotter than the last days. Let's keep excavating. I found something. This is definitely a worked piece of wood. I wonder from which time period it originates. This wooden tool could be from an early dynasty, but also maybe very modern. I also cannot find any inscription. And there is also absolutely nothing around here that could give me a clue from which time period this tool comes from. I know what I will do. I go to a C14 laboratory so I could have it dated there. Why don't you come with me? Hello, I'm looking for a C14 laboratory. Am I here at the right place? Yes, exactly. You are here at the right place. How can I help you? Very good, because I found this clearly worked piece of wood, but I don't know from which time it is. A tool like this could be from the earliest dynasties, or also very modern. I really don't know. But you look like an archaeologist to me. Can't you tell from the type of the wood, or the style of the artifact from which time period it is? Yes, I am an archaeologist, but a tool like this was used in all dynasties, and there's also no inscription on this piece of wood. And additionally, the archaeological context, so the place where the artifact was found, does not help, because there was nothing around there except this artifact. So I would need a C14 analysis for this organic piece of wood, so I can determine the age of this tool. Anyways, you need to give me some kind of time range from when this artifact could be. Otherwise, I cannot determine the age of it using C14. What? Why is that? Do you see this equation here? In this equation, you have to put the C14 concentration of the artifact when the organism died, so the tree was cut off. This corresponds to the C14 concentration in the atmosphere in that time. Otherwise, you cannot determine the age of the artifact. But if I would know when the tree was cut down, I would also already roughly know how old the artifact is, so I wouldn't need a C14 analysis. Yes, but without an estimation from your side, I cannot do any calculation. So are you telling me that I need to know how old the artifact is in order to calculate how old the artifact is? Yeah. Yeah, sort of. Welcome back to another episode of Rethinking Evolution Theory. In this episode we will discuss the probably most famous chronological dating method, namely the carbon dating method, which was developed by Libert Frank Libby in the University of Chicago and published in 1955. You often encounter this method in schools in mathematics classes when learning about exponential functions. Let's go through the theoretical idea of it. What you can see here is the Earth with its atmosphere. If cosmic rays, represented here by the yellow rays, hit the Earth's atmosphere, neutrons are created in the uppermost layers of the atmosphere, which are represented here by the dark violet dots. When these neutrons in turn hit the nitrogen elements, which make up the largest part of the Earth's atmosphere, a certain amount of C14 isotopes and protons are created according to this equation. This C14 enters the plants through interaction with the atmosphere. And as you can see in this example, this tree absorbs C14 through photosynthesis. For keeping things simple, it is assumed that the tree, as long as it is still alive, has the same concentration of C14 as the Earth's atmosphere. And once the tree dies, it can no longer absorb C14, and because C14 is radioactive, the C14 it has already absorbed decays into nitrogen. Let's say someone felled this tree a long time ago and made a sarcophagus from the wood of the tree. And we now want to determine the age of the sarcophagus using radiocarbon dating. The more C14 is present in the wood of the sarcophagus, the younger it is, and the less C14 is present in the wood of the sarcophagus, the older it is. We would have to use the equation we deduced in episode 2. For this calculation we need N of T, the C14 concentration which is now present in the wood. This is not a problem, because this value can be measured any time. And here we can insert the known decay constant lambda of the C14. And as you can see, we are back to our familiar problem from episode 2, which is the initial length of the candle. Because here we also need the C14 concentration of the tree when it was felled, which corresponds to the initial length of the candle from our thought experiment, and which is unknown to us because no one was there to measure the C14 concentration when the tree was felled. Libby assumed that the intensity of the cosmic rays, which produce the radioactive C14 from the nitrogen in the atmosphere, remained constant over 20,000 to 30,000 years, and thus the C14 concentration in the atmosphere was the same as today. According to Libby, the current C14 concentration in the Earth's atmosphere could therefore simply be used for this calculation. However, no one can confirm this assumption, as no one was present to measure the C14 concentration during this period. The intensity of the cosmic rays could have been higher, and therefore also the C14 concentration in the Earth's atmosphere. Or it could have been lower, and thus also the C14 concentration. Libby writes in his work, "The question of the constancy of the cosmic radiation intensity is much more difficult to answer. One feels that it is not unlikely that the intensity has remained constant in the sense we demand. Namely, variations in the average intensity over periods commensurate with the lifetime of radiocarbon. Since it appears to be a phenomenon originating in the cosmos and therefore probably tied to the timescale similar to that controlling the intensity of solar radiation. However, it is not obvious a priori that it is true, and we must admit the possibility of variations having occurred." In this section, Libby describes how, in his own opinion, the cosmic radiation has been probably remained constant as required or desired. However, he writes further that one must admit the possibility of variations cannot be ruled out. But feelings don't count in science. The very language and word choice in this section that Libby uses, like "one feels" and "we must admit," demonstrate an unscientific approach and a certain wishful thinking, which leads to fitting idealizations into calculation models in whatever way best suits the situation. Measurements of the C14 concentration of the Earth's atmosphere over the following decades have shown that Libby's assumptions were incorrect, and that there is a significant change in the C14 concentration of the Earth's atmosphere over the time. This leads us to a logical problem. If the C14 concentration in the past was not the same as today, we would need to know the age of an unknown organic object, so we could determine when the object or the living being died, in order to put the corresponding C14 concentration of the Earth's atmosphere in the equation. Which means we would need to know when the living being lived, so we can calculate when the living being lived. Which makes of course no sense. When I know when the living being lived or died, I don't need to calculate when it lived or died. Even if we had the C14 concentration of the past millennia, this would not help us, because we still need to know the time of death of the organism for putting the corresponding C14 concentration of the Earth's atmosphere here in the equation as an initial value for the C14 concentration in the died organism. This makes the C14 method an useless method, because it cannot lead you to any surprising result. Nevertheless, we will discuss the attempt of measuring the C14 concentration of the past via the so-called dendrochronology, in order to draw your attention on the problems of the assumptions and the presuppositions of dendrochronology. I would like to emphasize again that even if one knew the C14 concentration in the atmosphere over the last thousands of years,
the C14 method would not be a valuable method because one would have to know the age of the object in order to calculate the age of the object, which of course makes no sense. Hans Eduard Suess tried to use tree rings to determine the carbon concentrations of the past. The discipline of generating chronological information of the past through tree rings is called dendrochronology. If one assumes that tree rings contain information about the composition of the atmosphere of the past, one must again make some assumptions and idealizations. Before we turn to the assumptions of dendrochronology, let us first consider further the assumptions that Libby used for the C14 carbon method, so we can compare them then with the assumptions of the dendrochronology of Hans Eduard Suess. For Libby, rapid mixing processes are important because they allow him to argue for a sufficiently steady state of the C14 concentration in the atmosphere. A time-dependent C14 concentration would mean that you would first need to know the C14 concentration in the atmosphere when the organism died in order to calculate the age of a sample. Therefore, one must know when the organism died in order to calculate when the organism died. In the chapter Worldwide Distribution of Radiocarbon, Libby describes the distribution of radioactive carbon in the atmosphere depending on the altitude of the atmosphere and the Earth's magnetic field, which also had to remain constant for thousands of years for assuming an equilibrium in the system. Libby writes, "The time for radioactive carbon dioxide in the air to distribute itself through this reservoir probably is not in excess of 500 years. This is the so-called turnover, time for the life cycle, which has been widely discussed by geochemists. The estimates vary quite widely, but it does seem that this time can hardly exceed 1,000 years. Since this is a time short as compared to the lifetime of radiocarbon, we conclude that any given radiocarbon atom will make the round trip several times in its lifetime. And we therefore predict that the distribution of radiocarbon throughout the reservoir will be quite uniform, there being little vertical or latitudinal or longitudinal gradients left." Libby argues that the mobility of radioactive carbon is very fast and high compared to its long life, leading to a uniform distribution across carbon reservoirs. A particular attention is paid to the interaction between the carbon content of the oceans and the atmosphere, which he considers one of the main factors for the distribution of carbon, and strongly depends on the temperature of the oceans. Libby admits that an estimate on the influence of this interaction is difficult, but he nevertheless attempts to account for it using a correction factor. Suess also mentions Libby's argument for rapid mixing of the atmosphere, which is not allowed to be true in and around a tree trunk if one wants to derive information about the C14 concentration from the tree rings. Ideally, the exact opposite assumption of Libby would have to be made for trees, namely that no mixing effects occur between the trees and the atmosphere and between the tree rings themselves. Libby argues this through the covalent bonding of organic molecules, which make the exchange of carbon less likely. This might make sense if one assumes that the carbon is bound in the wood cells. However, when a tree is felled, it is moist across the cross-section. To produce usable wood materials, wooden boards must be stored in drying chambers for hours. This raises the question, is this liquid pure water? Or does it also contain carbon that could be distributed across the cross-section through possible mixing effects? Furthermore, the influence of so-called medullary rays, which ensure radial mass transport and mass storage in the tree trunk, must be considered. This radial mass transport complicates the relative age determination of the atoms. Another question is whether the bound carbon atoms in the cells originate exclusively from the atmosphere or whether the carbon atoms are also absorbed from the soil. If atoms also enter the tree from the soil, a dependence on the soil conditions must also be considered. Suess writes, "The dendrochronology dates were based almost entirely on the bristlecone pine tree chronology of C.W. Ferguson, from which we had obtained almost all investigated wood samples." C.W. Ferguson uses trees from the northwest of the USA for his chronology. White Mountains, California. California is a state in which forest fires occur very frequently. and in which forest fires must have burned for long periods of time in the past, as they have not been extinguished by humans over thousands of years. What effect do such forest fires, which emit smoke from burned wood of different ages into the atmosphere, have on the trees of this region? These gases, which partly consist of carbon of different ages, can penetrate into the tree trunks via so-called lenticels, and also can be absorbed through photosynthesis. Why does the rapid mixing of carbon end at the trees? Mixing processes are not only possible between gases and liquids. Suess describes that the atmosphere mixes within 2 years, but that a small geographical dependence of the C14 concentration cannot be denied. As you can see, completely opposite assumptions have to apply for trees compared to the atmosphere, which reflects a certain wishful thinking. 1,000-year-old trees aren't also found in every region of the earth. So how much sense does it make to date a sarcophagus from Egypt using trees from California, as Libby did? Let's return now back to Libby's assumptions, which focused particularly on the interaction between the oceans and the atmosphere. However, the C14 concentration in the atmosphere and the oceans is far from only dependent on changes in the ocean volume and temperature. This is just one of many natural effects and phenomena, which are difficult or impossible to estimate, that influence the C14 concentration in the atmosphere. Further examples of such variable influences and phenomena include, as we already mentioned, the intensity of cosmic rays, including the intensity of solar rays and forest fires, the chemical element composition of the Earth's atmosphere and the oceans, changes in the Earth's magnetic field, the extent of ozone holes, different flora and fauna with different metabolic interactions with the environment, meteorite impacts, volcanic eruptions, hydrothermal vents, climate change, and so on. Therefore, one would have to know the course of countless variables that are beyond human chronological reach in order to develop a useful model. These variables also interact with each other, which further increases the complexity.
We are now at the end of our episode. I hope you liked it and that I see you in the next one. Bye!